We know that as we grow, the hurdles will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way, keeping odds. Okay, so in module number 5, we are going to discuss the second part of Scott connection of three-phase transformer. Previously, we have determined the voltage ratio relationship, phasor diagram, and the position of neutral point N. Today, in lecture number 5, we are going to discuss that relationship between input and output current. Okay, so as we have mentioned in our first part of Scott connection of transformer, so this is the main transformer primary, and this is the main transformer secondary, and this is the teaser transformer. So two single phase transformer are used to three phase to two phase conversion and vice versa. Now if we see here, this is IM. So IM is the current in the primary of the main transformer, primary current, and this is for main transformer. Okay, similarly I2M is the current in the secondary of the main transformer, and similarly for teaser transformer also, one is this is I1T, so current in the primary of teaser, primary current, and this is I2T, so I2T is the secondary current of teaser transformer. And if you see here, IA, IB, IC are the line current of the three phase side. So IA, IB, IC are line current of supply side. Okay, now if we see in this figure, we can say this IA equals to I1T. So from here we can conclude that IA equals to I1T. And I have mentioned in my first lecture that secondary for this teaser as well as for this main transformer is identical. So if this is identical, so from here we can conclude I2M equals to I2T equals to, let's say we will assume this as I2. Okay, so this is I2. Now let the in this determination of relationship between input and output current of Scott connection, we will neglect the magnetizing current. So magnetizing current we have neglected. This magnetizing current. This is neglected. Okay, so from MMF balance of the teaser transformer, so if we see in the figure, so this is the teaser transformer. So MMF balance I want to apply. So current is I12, turns ratio is TAD because this part is AD. Okay, this part is AD. This, so I1T
into TAD, because this is AD. So turns is TAD equals to I2T into TS. TS is the secondary number of turns of TZ transformer. So we got this relation. Okay, so that means let me write it once again. I1T TAD equals to I2T TS, MMF balance of TZ transformer. This is MMF balance equation of TZ transformer. So we have discussed previously I1T equals to IA, and we know TAD equals to root 3 by 2 TP. This is we have deduced in my first part of Scott connection, equals to I2T into TS. So IA equals to I1T equals to 2 by root 3 TS by TP I2T equals to 2 by root 3 I2T by A, where A is the turns ratio. Okay, and I2T equals to root 3 by 2 into TP by TS into IA equals to root 3 by 2 IA. So we got these two equation. Okay, let me name it as 1 and 2. Now similar MMF balance equation we will apply for main transformer. Okay, so that will become IB into TP by 2 minus IC into TP by 2 equals to I2M into TS. Because if we recall the figure, so this is B phase current, so IB into 0.5, that is TP by 2, minus IC into TP by 2 equals to the secondary current I2M into TS. Okay, so that is what exactly we have written. So from here we will get IB minus IC equals to 2 into TS by TP into I2M equals to 2 into I2M by A. I2M equals to and half TP by TS into IP minus IC. So this is equation 3. So this equals to A by 2 IB minus IC. So this is equation 4. Now this is for a 3-wire system. From basic electrical knowledge we know for a 3-wire system, IA plus IB plus IC equals to 0. So IC equals to minus of IA plus IB. Now we will substitute this value of IC in the equation number 4 here. So you put IC value here. So you'll get equation number 4 and also in the equation number 3 here and here. So you'll get IB plus IA plus IB equals to 2IM by A. IB equals to minus IA by 2 plus I2M by A. Now we got the value of IB. So we put this value, substitute the value of IB in this equation, equation number 4. So we put the value of 5 into 4. So we will get that in this equation we will put this equation here, in this equation IC equals to minus IA minus IB. We will put the value of IB, not this equation number 4 but this equation number say 6. So put 5 in 6. We will get IC equals to minus IA plus IA by 2 minus I2M by A. So that means minus IA by 2 minus I2M by A. This is equation number 7. So in the above equation, or rather we can say in the above treatment, it has not been mentioned whether the transformer is converting from 3-phase to 2-phase or 2-phase to 3-phase, but this both modes are possible. Now if we see equation number this I2t equals to, where it is, I2t equals to 3 by, so this one I2t equals to root 3 by 2 TP by TS into IA, that is root 3 by 2 AIA, and equation number this, it is I2M equals to this I2M equals to A by 2 IB minus IC can be solved for 2-phase current. That means we will get the value of I2M, I2T. So this is for 2-phase current when the 3-phase currents are known. Similarly, equation number this, that is IA. So here this equation IA equals to this root 2 by root 3 I2T by A. Equation number IB we will get here this IB equals to this, and we get the value of IC. So from here we will get the value of IA, IB, IC for 3-phase current. For 3-phase current, when these two values are known, I2M and I2B. So when 3-phase current is known, this will give the value of 2-phase current. When 2-phase current are known, this we will get for 3-phase current. And these equations are valid for both balanced as well as unbalanced load. Okay. So now let me draw the phasor diagram for balanced load. So let me first draw for 3-phase side. So let me draw first for 3-phase side. Okay. Let me draw the 3-phase side. So this is A, this is B, this is C. Okay. This is my IA in 120 degree. This is my IB, and in again 120 degree, this is my IC. So from the equation, so IC is equals to minus I2M by A minus I2M by minus IA by 2. So this is my minus IA by 2. Similarly, for this IB equals to, this is minus IA by 2. So IB equals to minus IA by 2 plus IM by 2A. So if this is minus IM by 2A, obviously this is plus I2M by A. So this is for 3-phase side, and for 2-phase sides the phasor diagram is this is V2M, this is V2T, lagging power factor, current lag. So this is I2T, and this is I2M. So these are the power factor, angle phi, and this is 90 degree. So this is for three-phase side, and this is for 2-phase side. Okay, so this is the phasor diagram for balanced load. Now if the 2-phase current are balanced, the 3-phase current are also balanced. Okay, so let me prove that if 2-phase current are balanced, 2-phase current are also balanced. Now since the two secondaries are identical with TS number of turns, we have mentioned several times, then we can write that I2M equals to I2T equals to I2. We have already assumed this one. Okay, now let this I2T as reference. So what will be my I2T? I2T equals to I2 angle 0 degree, because I have taken this one as reference. So what will be my I2M? I2M equals to I2 minus 90 degree, balanced 2-phase supply. That means in complex notation J I2. Now we have seen that IA equals to, we have just deduced just few minutes back, IA equals to 2 by root 3 I2T by A. That means 1.15 I2T by A. So you can write down 2 by root 3 I2 angle 0 degree, because I2t equals to I2 angle 0 degree. So I equals to 2 by root 3 I2t by A. Okay. So from similarly we will get the value of IB from this equation, equation number 5, and we will get the value of IC from this equation, equation number 7. So we will get the value of IB equals to minus half IA plus I2m by A. We will put the value, that is will become, if we put the value of angle, that is I2 by angle 0 degree, so it will become minus 1 by root 3 I2 by A angle 0 degree minus J I2 by A. So if we simplify this, it will become 2 by root 3 I2 by A minus 120 degree. Similarly, from the equation number 7, we will get the value of IC equals to 2 by root 3 I2 by A angle plus 120 degree. So if you see that IA, IB and IC magnitude is same, 2 by root 3 IA by 2. So magnitude is same for all the current. IA equals to IB equals to IC equals to 2 by root 3 I2 by A. And if you see that this is 0 degree, it is apart minus 120 degree, this is minus 240 or plus 240 degree, and this is the criteria of balanced three-phase system. So that means we can say that if two-phase load is balanced, the three-phase input is also balanced, and the opposite also true. For a two-phase balanced load, that I2t equals to I2m, secondary side. Okay, I2t equals to I2m equals to I2, which we have assumed previously, and we have shown the respective phasor diagram. Now from this phasor diagram, we can say that IB mod of IB equals to mod of IC equals to root over of I2m by A whole square plus I1t by 2 whole square, and that is becoming mod of IA equals to mod of I1t. Okay. So this is for balanced load. Unbalanced load also we can deduce in the same fashion. And what are the application of this squat connection? It is basically applied for a single phase loads such as electric trains, which are so scheduled as to keep the load on three phase system as nearly balanced as possible. And also this is used in electric furnace installation. So this is all about Scott connection. Okay, so this is all about Scott connection. So these are the reference book. You can follow these books. Also you can read the book of electrical machines by Ashfaq Hussain. So you can read this. Okay, thank you.